microphone activated yet? Or I guess it's not sure.
Greg, that one is.
Okay, I suppose I can use that. I have.
Oh, you got that one?
Yeah, I have the one that.
Okay,
Okay,
great.
great.
Good to go.
Everyone hear me? Okay, well, maybe I'll start with the other microphone and see if this one is live. Ever.
You just gotta turn that one on.
I think it's on.
No, the black physical.
Oh, this one.
Yeah,
Gotcha.
there's a little switch on the mic.
Gotcha. Is this one on? It doesn't seem to be doing anything.
Yeah, let's see. It should be on.
Okay. Can people on Zoom hear me through this mic?
Yes.
Oh, okay, wonderful. Awesome. Great. Then I think, are we all set to start?
Yeah, why don't I just quickly introduce you and then
Sure.
we can get started. So the next talk will be given by Greg Meyer, and he's going to tell us about classical verification of quantum computational advantage. So please, Greg.
Awesome. Thank you so much for the introduction. Yeah. Also, thanks so much for inviting me. I'm super excited to give this talk. This is some work that I've been doing with my advisor in the physics department here at Berkeley, Norm Yao, as well as with Umesh, and also with Soonwon Choi, who was a Miller postdoc here at Berkeley and is now faculty at MIT. So, right. Oh, let's see if we can advance the slides. There we go. So right, today what I'm going to be talking about is this idea of black box proofs of quantumness. So this is an efficiently verifiable test that only a quantum computer should be able to pass. And to be just like a little bit more formal about this, we can imagine defining it sort of like any other, computational proof that we're going to do, where we have a completeness claim where we say that there exists some BQP prover that causes the verifier to accept with high probability, and that for all BPP provers, the verifier accepts with low probability. And I think this is kind of like a fun thing because it's not like we're trying to prove any particular statement or anything like that. What we're really trying to demonstrate is that, we're contained in or we have some particular computational power. And so there's a few things that I'd like to emphasize here. So the first is that in this situation, the verifier is fully classical and also the communications are fully classical. So we never allow, any amount of, measuring like single qubits or something like that. The prover is a single black box. So, Urmila mentioned that there are some protocols in which we have, two provers that can't communicate, and this gives us some extra power. But in this case, like in the talk that Urmila was giving, we're just going to use computational assumptions and interact with a single sort of like classically communicating black box. And sort of something that I think is kind of neat is that the soundness proof doesn't actually know anything about quantum mechanics. So what we're actually trying to do really is disprove the null hypothesis that the prover we're interacting with is classical. Really, I mean, the model of computation that we know might be able to do this is quantum mechanics. So in some sense, it's a proof of quantumness, but maybe to be slightly more precise, we would even call it like a proof of non-classicalness. So there's a couple of situations in which this sort of test might be interesting. One is just to do like a really powerful refutation of the extended Church-Turing thesis. So of course we have these experiments, where like random circuit sampling and boson sampling, where there's kind of this Goldilocks regime that people talk about, which is where, okay, if you do random circuit sampling and there's no way to efficiently verify it, you can go to a problem size where you can demonstrate an advantage. So, your quantum computer solves it quickly, but it takes a really long time for a classical computer to solve it. But it's still small enough that you can throw a whole supercomputer at it and like check that the results actually make sense. But in this case, because we have an efficient verifier, we can, go to the regime where it would take the lifetime of the universe for a classical supercomputer to solve it, and then, still be able to check it on our laptop, which is kind of a nice feature. The other situation in which this sort of thing might be useful is just, you have some cloud service that claims it's, running a quantum computer, and you want to make sure that they're not just secretly, simulating all of your circuits or something like that. So you can just send some data back and forth through the internet, and then after doing this, be confident, okay, this is actually, they actually have some quantum power. So Turns out there's an easy way to do this, which is just to run Shor's algorithm. You multiply two large primes together, send them to the prover, and ask for the factorization. So good, that was a good talk, very efficient, and that's it. But obviously, we want to do something slightly more interesting than this. And the reason is that we want to do it on a near-term device, right? So we want to be able to demonstrate this sort of thing without resorting to quantum algorithms that are not feasible on today's devices. And in terms of doing this on a NISQ device, there are kind of two broad paths that we might take. So first of all, we could take one of these sampling problems, like random circuits or boson sampling, which is feasible on a NISQ device, which people have already shown in experiments, and then figure out a way to add some structure to it or something like that to make this sort of problem have an efficient verification scheme classically. The other thing we can do is we can take one of these, number theory problems or other algorithms, which, we know a quick, efficient way to verify it, but seem hard on a NISQ device, and figure out some way to make it less costly so that we can achieve both of these goals, that it's both NISQ feasible and efficiently verifiable. So yeah, for the rest of this talk, I'm going to be talking about not sort of, proofs that this sort of thing exists, but essentially ways that we can make it faster and make it feasible to do in the near term. Okay, good. So first I'm going to talk about this idea of adding structure to sampling problems. Generically, this idea seems pretty hard because, in some sense, the point of doing, like random circuit sampling or something like this is that it doesn't really have structure in it, mixes things up really quickly. And that's why you're able to do a classically hard test in a short amount of quantum volume or something like that. Just as an example, there was an idea of sampling IQP circuits, which is, Hamiltonians that have this sort of structure where we have just products of Pauli X's on various qubits. And about a decade ago, it was shown that, you can hide a secret in this Hamiltonian H such that you evolve for a certain amount of time and then sample the resulting state. And then you're going to get some results that are correlated with this secret. And a little bit later, there were actually a number of papers that showed, that classically simulating these Hamiltonians is hard, and average case complexity is just as hard as worst case and things like that. But the fundamental thing that was sort of still open is that this hiding relied on non-standard cryptographic assumptions, and it wasn't clear if this actually works. And it turns out that this doesn't actually work. In the sense that there is a classical algorithm you can use to extract this secret from H. So this is just sort of an example to demonstrate that while this is potentially a promising way to go about things, it seems that it does open a lot of opportunities for classical cheating, and it's not totally obvious how to, sort of encode standard cryptographic assumptions into these sampling problems in a way that allows the sampling problem to still be easy on a quantum computer, but have some cryptographic weight behind it. So for the rest of this talk, I'm going to focus on the other path, which is to take one of these number theory problems like factoring, discrete log, something like that, which perhaps have some efficiently verifiable protocol, and see what we can do to make them less costly and make them NISQ feasible. Okay, so the starting point is actually going to be, was already very nicely introduced by Urmila. We're going to be working with these interactive proofs. So the sort of broad structure that we're going to use is the following. And this is just kind of something to keep in your head. The first round of interaction is going to involve the prover committing to a specific quantum state. And then the rest, either one or a couple more rounds of interaction will involve the verifier specifying to this prover how to measure that state. And it turns out that this kind of structure is actually super duper powerful in this context, because the nice thing about an interactive proof is that you can randomize the later queries, or and I mean, you could also have it be adaptive, but in this case, we're not going to worry about that. And by doing this, you can ensure that the prover would respond correctly, essentially, no matter which measurement basis you request. The thing that's really neat about this is, you can only make really one measurement of a quantum state. If you're doing a full measurement, then you collapse and you're done. But by doing this randomization and ensuring that the prover would respond correctly no matter what basis you ask for, you can almost do a sort of like virtual tomography where you like hide some cryptographically secret information in the state. And then what you're saying is, okay, I know that the prover actually was holding this information that we cared about, even though maybe any single measurement wouldn't be able to give me anything cryptographically meaningful. Okay, so this is really cool. And this kind of stems out of the first original protocol that Ermila was talking about, which I'll just go back over really quickly, just so that we have an idea of where we're starting from. So how does the prover commit to a state? We're gonna use this this idea from that first paper that was being discussed. So you take a 2-to-1 collision resistant or claw-free function. Here, we're considering it one single function. It's kind of equivalent to say, you have two functions, f0 and f1. You can just add the single bit to the front to make it into one function. And we're going to do this thing that was discussed in the previous talk, where the verifier picks such a function, sends it over to the prover. They evaluate the function on a uniform superposition of the inputs. And then they're just going to measure this second register, store that as a value y, and send it back to the verifier. So the reason that this is really neat is that by measuring this, we're going to collapse onto a uniform superposition of these two preimages, x0 and x1, which we know are cryptographically hard to hold at the same time. But because the verifier holds a trapdoor, they're able to compute the state in full. So now the verifier knows the whole state, and the quantum prover's job now is to demonstrate to the verifier that they actually hold this state and they didn't just make up some y and then send it over. So right, so in this talk in particular, we're kind of going to stick with this commitment strategy rather than modifying it like Ermila was doing. And we're going to talk more specifically about the measurement scheme we're going to use on this state. So, okay, so this is the first round that I just talked about. How are we going to measure this state? This is the original protocol from these 5 authors that Ermila was already discussing that you can build based off of LWE. Essentially, what we're going to do is just pick the standard of the Hadamard basis, send it over to the prover. The prover is going to measure each of the qubits in the superposition in that given basis and send the result back, and validate that result against x0 and x1. So this works for the TCF based off of LWE, but there's a little bit of a subtlety, which is that the claw-free nature of this function f does not actually imply that it's hard to come up with these measurements directly. In this specific case, the LWE TCF has this special cryptographic feature called the adaptive hardcore bit. And what this says is effectively, it directly proves from a cryptographic standpoint that it's hard to come up with these two measurements at the same time. And as Ermila described it, this is just saying that essentially if you know one preimage, you can't even come up with one bit of the other preimage. Well, in this case, we're just trying to say that what we'd like to say is that if you know one preimage, you can't come up with the other preimage in full. Okay, so since this original protocol, there have been a number of other trapdoor claw-free functions that have been suggested for use in a protocol like this. But we can see that all of them, as far as we know, other than LWE, don't have this adaptive hardcore bit property. So there's this question, what sorts of protocols can we build that doesn't require an adaptive hardcore bit? And there was a nice work last year, which shows a protocol that both is non-interactive, so it's down to just you send a message and bring it back, and also doesn't require this adaptive hardcore bit. And this was proven in the random oracle model. We might ask then, is there a way that we can remove the adaptive hardcore bit in the standard model for doing, for example, this rigorous refutation of the extended Church-Turing thesis? So the answer is yes, and that's the protocol that I'm going to talk about now. So just to remind us, we're going to start from the same protocol that we had before, where we're measuring in the standard or the Hadamard basis after committing to a state, and then sending back the result. But we're going to keep this measurement in the standard basis as one of the options. But instead of measuring in the Hadamard basis, we're going to replace it with this thing that we call the one-player CHSH game, which I'll describe in a moment. So as we kind of go through, at this point, the verifier picks standard basis or play the one-player CHSH game, and we can show that with this measurement scheme, you actually don't need the adaptive hardcore bit. So I'll explain what I mean by this now. So what we're going to do is add one more round of interaction in this case, and the 2 rounds are going to be the following. First, we're going to condense the information held in X0 and X1 onto a single qubit, and then we're going to do something that's the equivalent of a Bell test on this qubit. So, which might seem kind of out of left field, but I'll explain what I mean by that. It seems, I like it. I think it's pretty cool. So what the verifier does for this first step, this condensing step, is to pick a random bit string, R, send it over to the prover, and then this right register here is just a single qubit, a single ancilla. They're just going to compute the inner product of X with R in this ancilla. So you can just do this easily by applying C0 gates from this X0, X1 register over into this ancilla. Then they're going to measure all of the qubits in this X0, X1 register in the Hadamard basis, which kind of, erases it and applies some phase, and send the results of that measurement back. So the thing that one can see if you work through this is that after this, after performing this operation, you'll end up with a single qubit state that is either 0 or 1 if this equality is true, if x0.r is equal to x1.r, or plus or minus if this is not true. But it turns out what you can show is that this equality is actually protected by the cryptography. So just from the fact that we have a claw-free function where it's hard to come up with x0 and x1, we can use the Goldrick-Levin theorem to show that this it's cryptographically hard to get any advantage in determining this equality. So essentially what we're saying then is cryptographically we're protecting whether the qubit is polarized in the Z basis or in the X basis. Now this might feel a little bit useless because you say, okay, but both of these are maximally mixed states, right? So like how can we do anything meaningful to distinguish them? Well, it turns out in the CHSH game or in a Bell test, after you measure one of the qubits, the other qubit is also in a maximally mixed state. But what you can do is generate some correlations that even if they don't tell you anything about the state, you can still prove that there was some kind of correlation going on there. So just to make it very clear, in our case, the polarization of this qubit is hidden by the cryptographic secret, and in the CHSH case or the Bell test case, the polarization is hidden by the non-communication between the two measurements or the two parties that are playing the game. So it turns out we can kind of go straight through and just do what you would do in a Bell test or in the CHSH game. We pick an intermediate basis like the Z plus X or the Z minus X basis, send it over to the prover. The prover measures the qubit in that basis and sends a result back. And then you can just validate against these various quantities that you've gotten and get some correlation with the cryptographic secret. And so just like in a Bell test or in kind of any interactive proof, you can come up with a classical bound for success. So, if we collect statistics after, running the protocol sequentially many times, we can compute 2 values. It turns out for the analysis, it's easier to keep them separate. The success when you're just, getting a pre-image in the standard basis versus when you're playing this CHSH game. And so this is the bound under the assumption that the function's claw-free. And then if you walk through the case of the ideal quantum prover, running the protocol honestly, you can show that you end up exceeding the bound by a fair amount. And one cool thing that I just wanted to point out is that if you just hold the probability of getting that standard basis measurement right at 1, then sort of like, so that's for both the classical and the quantum prover, then you can look at the probability of winning the CHSH measurement and you actually recover the exact win probabilities that you have in that normal game, which is kind of nice. Okay, so this is the protocol, but the whole reason that I said we were doing this was to make it feasible for near-term devices, right? So you might be wondering, like, what can we do on near-term devices with this? And it turns out that there are, with this protocol or with, the random oracle model one or any of these protocols, there are kind of 3. Okay, the one round protocol doesn't have this issue, but there are 3 main challenges. So one is partial measurement, right? If you're going to do an interactive proof and you're sending classical data, you have to make some measurement in the middle, send it over, and then wait for a new response, and then do the next thing. there's also this fidelity requirement, right? So you need to pass the classical bound that I mentioned. And I'll show that, a sort of generically, if you run the quantum prover and it just has a little bit of fidelity, it will be significantly below the bound. It won't be like saturating the bound. So we need to figure out how to deal with that. And then lastly, you need to run these circuits that evaluate this trapdoor claw-free function on a quantum device. And it's not at all, obvious like how to make these circuits efficient. Okay, so for the partial measurement thing, I just wanted to use this to highlight some really cool experimental work that's going on. So some folks at the University of Maryland, soon to be moving to Duke, have been working on demonstrating these protocols in trapped ions. This is the team, among other people, and also, on the theory side, we've been working with Thomas and Umesh and other folks on this as well. So the main thing I wanted to show here is that it turns out that partial measurements in the lab are actually coming along pretty nicely. And in this trapped ion system, it turns out what they can do is take their chain of ions and actually modify their traps so that the chain splits in half. And then they zap one of these to measure it. And it's far enough away that it doesn't actually decohere the other set of ions. And then they bring them back together and do whatever rest of the computation they need to do. Which is really cool. It seems very hard. These are the moments that I'm happy that I'm a theorist, because experimentalists seem like they have a very difficult task in front of them. But yeah, it turns out that partial measurements with high fidelity are starting to come along well. And it feels like this is kind of, coming along in the experimental setting. The high fidelity requirement is something we can help out with on the theory side, it turns out, by doing a kind of post-selection based technique. So as I mentioned before, it turns out if you kind of like do the math, to pass this classical bound, you need an 83% circuit fidelity if you're just sort of generically running the circuits for this problem, which is quite high, right? Like we'd like to be able to pass it with like only a little bit of fidelity. For example, the random circuit sampling experiment, ended up with a cross entropy benchmark of like 0.2% or something. And that was enough to show that there was a quantum advantage. So we'd like to be able to do a similar thing here. It turns out you can show that if you can get your prover to hold this state with this phase in between x0 and x1 kind of only having epsilon coherence, so it might be plus, it might be minus, but it's plus just like epsilon more of the time than it's minus, then you can pass the test. So then the question becomes, is there some way we can get our prover to generate this even if it's noisy? And it turns out you can. Essentially what you can do is make sure that f of x has a bunch of redundant bits in it, and then you just post-select on these values f of x after you measure them in the first round, and make sure that they're valid, right? And the assumption that's kind of implicit here is that if there's some sort of corruption in the circuit that evaluates f of x, then that'll show up as corrupting this output bit string. And I'm not going to spend too long on this, but I just wanted to show that we did some numerical experiments and showed that sort of as we add more and more redundancy, which is measured by this value m here, we're able to kind of push up this curve. The x-axis is the total circuit fidelity, and this line here is the threshold for demonstrating advantage. And we're able to push up this curve, and as we add enough redundancy, this post-selection scheme allows us to kind of bend the curve and keep it always above the quantum advantage threshold. So even with only 1% circuit fidelity, we can still pass the classical bound. Okay, good. So the last thing that I mentioned that I wanted to handle in terms of making this thing feasible for near-term experiments is that we have to actually evaluate the TCF, right? This is kind of like the thing that's been looming over us. How are we going to do this? So getting rid of the adaptive hardcore bit certainly helps because it opens up these trapdoor claw-free functions based off of x squared mod n or ring LWE that have really fast classical circuits. So asymptotically, you can get them as fast as n log n, though whether that's feasible in practice is another question. But the issue here is that these classical circuits, these algorithms are recursive. So it turns out that they're really hard to make reversible because you have to store the outputs of each level of recursion. So then when you continue to recurse, you can uncompute them later. The really beautiful thing about actually all of these protocols, basically any protocol in which you measure the second register and then have a polynomial number of bit strings superposed on the first register is that there's actually a way to make these circuits irreversible with adding essentially no overhead to the classical circuit. And I'll show how to do that now. So normally, right, when we convert just a classical circuit to a quantum circuit, we have these garbage bits hanging around. So if we take, an AND gate and we want to turn it into a Toffoli gate, we have these inputs that we have to maintain. Otherwise, the gate won't be unitary. And in general, if we take an entire classical circuit and turn it into a unitary, one way we can do it is just kind of leave these garbage bits hanging around. So this is like a circuit that's related to the UF that we want, in which we just evaluate the classical circuit, starting with these inputs X, these input qubits, have the output qubits f of X, and then we just have all of these extra outputs hanging around, which I've labeled GF of X, are the garbage bits. So I don't know if I would say standard, but a easy way to deal with this is to simply run UF prime of X, copy the result via C0 gates to some extra output register, and then run UF prime backwards. And then that'll uncompute f of X and GF of X, but because we C0'd the result out into this register, we can keep f of X around. Now, of course, this is not something that's a great idea in practice, because not only do you have to run your circuit twice, but also the number of garbage bits here could be, scales as the total number of gates in the circuit. So this can kind of like explode polynomially as you keep going. You don't want to use, this huge polynomial amount of space. Of course, there's, for many algorithms, more efficient ways to do this. You start uncomputing bits earlier, and there's this whole pebbling problem about, how to most efficiently do this. But the nice thing that I'll show is that there's actually a way to just avoid all of this in this specific context. And what you're going to do is just do a Hadamard gate on these qubits and then measure them. Okay, this seems like, the no free lunch theorem, like this is way too good to be true. How can you just do this? So let's look at what happens when we do this. We have the garbage bits, we do a Hadamard measurement, and we get some output string H. What we're going to end up with is this state where we have some phase, which depends on the outcome of the measurement and on the values of the garbage bits, on every term of the superposition. Normally, this is like useless, right? Because there's a unique phase on each term that depends on the X, and like you'd have to somehow like compute the phase on each term of the superposition to use it for anything meaningful. But remember that the next thing we're going to do in all these protocols is measure this value f of X and collapse onto just two inputs. And once we do that, G of X was based on a classical circuit, so the verifier can just compute it efficiently and then knows the phase in between X0 and X1, and then it's just easy to run the rest of the protocol without caring about what this phase is. So the takeaway here is that you can just directly convert classical circuits to quantum circuits with no overhead other than doing extra measurements. And so I've implemented x squared mod n using the Karatsuba multiplication algorithm, which is recursive. And for a 1024-bit multiplication in the abstract circuit model, it only costs 10 to the 6 Toffoli gates, which on the one hand is like way more efficient than doing a normal circuit for this sort of thing, and certainly more efficient than like running Shor's algorithm. On the other hand, 10 to the 6 Toffoli gates is still a lot of Toffoli gates, so we'd like to improve this. So with that, I'd kind of like to talk about the paths forward from these protocols. So the main bottleneck, which I hope I maybe convinced you of from the past few slides, is evaluating this trapdoor Clauffre function on the superposition. And I think fixing this problem and like running it, in the next year or something will require some kind of out of the box theory thinking. I don't think that the experiments are going to like magically be able to do this in the next year, though, hopefully not in too long. So some ideas, and I don't mean to like say that they're bad ideas because this is what I've been working on. So it's kind of sad if they're bad ideas, but so one thing you can do is try to find, say, more efficient trapdoor Clauffre functions or things like that. You can also, do these tricks that I was talking about, try to build better quantum circuits for them and that sort of thing. But like at a fundamental level, all of these trapdoor Clauffre functions are public key cryptography, right? And a lot of people have tried really hard to make public key cryptography fast because, we care about that in a classical context and that sort of thing. And, we want to use it on like RFID readers or like things like that. And it's not clear if like the best way to solve this specific quantum problem is to try to come up with, new public key cryptography that's like more efficient than the constructions that we already have. So maybe we'll want to take a slightly different path. So I call these box adjacent ideas because they are out of the box a little bit. So we find other protocols, maybe we can, take this IQP protocol I was mentioning and make it more efficient and also, make it rely on some standard cryptographic assumptions. Maybe, yeah, we can build something based off of, more efficient cryptography. Though, then you start to run into the question of, are you actually disproving the extended church Turing thesis if there's not if you're using cryptography that doesn't have a sort of complexity theoretic basis behind it. And then maybe there's some way outside the box idea, and I don't know, maybe there are many smart people in the room. Maybe they can help figure out some such way outside the box idea that will allow us to do that. So that's all I had. And I think we have like 9 minutes to discuss or chat. So yeah, if anyone has any questions or wants to discuss, happy to talk.
Thanks, Greg.
Thank you. First
Yes,
time giving an in-person talk in so long. It's nice. Sorry.
Well, thank you very much. This was really nice. So indeed, I think we have a bit of time for questions and discussion. Are there any questions? Either from participants on Zoom or there at Berkeley?
Yeah, sure.
Actually, two questions.
Sure.
First one is you mentioned that you don't need this adaptive hardcore bit anymore. So where did you avoid it? I guess I'm not familiar with where it was used before. And
Oh yeah, no worries. Yeah, let me maybe it's I can get back there this way. I just got to go through the trapped ion shuttling. So no, this is a good question. So right. So here where it comes in is that Irma mentioned that when you do this Hadamard basis test, you end up with this sort of equation test where you're saying you aren't able to come up with an equation that's like some string d dot x0 plus x1 equals 0, say, right? And where it comes in is it turns out it's not very hard to actually come up with a function that's just claw free where it's easy to come up with that sort of equation. Essentially what you can say is, or another way of saying it is to pass this test, you only need to know one bit of the other preimage after you know one of the preimages, or sort of like the parity of some subset of the bits of the other preimage. So that's fundamentally what the adaptive hardcore bit comes in, is saying that if you're going to do this Hadamard basis test, you need that output to actually be hard. And where you get around it is that when you do this operation, right, the hardness of figuring out this equality or getting some advantage in figuring out this equality depends on knowing every single bit of x0 and x1. And one way of looking at this is that, right, originally the prover was picking some string d and asking for the inner product between d and x0 and x1. Here instead, the verifier is picking that. So because the verifier picks it, the prover can't, pick some specific bits that they happen to know how to do something good with. The verifier just does it, and then they're stuck. So that's where it comes in.
so R is kind of like the analog of D.
Yeah, exactly. And it's a little bit confusing because there's this other D, because you do still do a Hadamard measurement on these things. So there's kind of two related things, but this D ends up just affecting the phase on these two. And since we care about the polarization and not the phase, that D that the prover comes up with ends up not mattering cryptographically. You can just kind of throw it away. Yeah. And you said you had another question, I think? Okay. Oh yeah, I think I see a hand raised on Zoom.
Right. So yeah, I think maybe Dan, do you want to ask your question? Dan Bernstein?
Actually, the Tanya part of Dan and Tanya. I was
Okay.
intrigued I was intrigued by the mentioning of other cryptographic primitives. Can you kind of pin down what is your cost function? So there is now some area of recent development where there's algebraic ciphers which are trying to reduce the number of multiplications, so the number of nonlinear operations. And that sounds a bit like it should be happy also for quantum computation.
Wow, that sounds, yeah, really great. I don't really know if I can like contribute too much in an answer to that. I guess to ask a quick question, what exactly do you mean by like, what do you mean by your cost function? Like, I guess, yeah, do you mind just clarifying a little bit?
Sure. I did my best in paying attention, but I probably don't grasp all the things that contribute to the expenses here. And so can you kind of summarize what parts are really expensive? So for instance, if I think computation I've been doing, but most of it was binary and you're working mod n. But I assume that multiplications are a lot more expensive than say additions, but you still have to do with carries. So that also sounds expensive.
Yeah, yeah. Okay, that's a really good point. So, right, there are kind of a number of different ways of of implementing this arithmetic, and there are some kind of inherently quantum algorithms that can improve on ways to implement this. But fundamentally, yeah, what you end up doing to implement, for example, x squared mod n is, so say take like the school book algorithm for multiplication, which it turns out actually performs pretty well for computing x squared mod n. You're just kind of doing the standard thing where you take, like products of individual bits and then like add them into a register and like sum up every individual product. And then algorithms like the Karatsuba algorithm, you're kind of like, breaking up the multiplication into several pieces and then using them in a clever way. But fundamentally, what ends up being expensive is just doing a lot of additions, or however you want to implement your multiplication. But in general, it's like the additions that end up being the fundamental cost. Does that help?
But you don't care about, say, ancillary bits, because Karatsuba is pretty bad for that normally.
Sorry, could you say it again? It's a little hard to hear you through the speakers.
Oh, but you don't care about, say, the space complexity, so you don't care about how many ancillars you need.
Oh, sure. You do certainly care about the space complexity, just in the sense that you don't expect near-term quantum devices to have, a large amount of space. So, for example, this is why I was saying in this garbage bit idea, you don't really want to just, run the circuit and then uncompute it by running it in reverse, because you end up with a polynomial number of bits. So it certainly is like very, very helpful to try to reduce the space complexity. And one thing that you can consider is sort of like the quantum volume. Like one trivial way to, or not trivial, but one easy way to measure it is just you multiply like the width of the circuit by the depth, and ask, and use that as kind of a rough idea of how expensive your circuit is, if that helps.
Okay, so then just as a recommendation, if you're looking for alternatives, maybe look at the algebraic ciphers from the symmetric crypto world. That could be interesting. Or shoot me an email if you want pointers.
Yeah, thank you so much. Definitely appreciate that. I'm excited to explore.
Okay, great. It looks like there are also two questions. They both look like good questions in the Q&A. Maybe I can just read them. So first, there's a question from Chining Chu, who asks, do you have an estimate about how many qubits are needed to demonstrate quantum supremacy using your protocol? For example, would a 256 qubit quantum simulator like the one from Lucan's group be enough?
Okay, really good question. Yeah, so what it comes down to is, which trapdoor clock-free function are you going to use? So, I also, we have in this paper a trapdoor clock-free function based off of decisional Diffie-Hellman, which is, kind of analogous to or closely related to the discrete log problem. And the nice thing about this is that if you do it over elliptic curves, you can kind of cut down the space by a lot. So I think you could show in sort of the abstract circuit model quantum advantage using like, I think it should be like 300 qubits or something. But the problem with this is you have to do elliptic curve cryptography in a quantum circuit. So, if you're trying to actually implement this, you're only using 300 qubits, but the number of gates you have to do is like super large. So this probably isn't super practical unless you can come up with some really, clever quantum way to do elliptic curve cryptography. On using x squared mod n, which has these fairly efficient quantum circuits, the issue you run into there is just that turns out classical computers are pretty good at factoring, even if it is ultimately, super exponential, or sorry, super polynomial. You need probably a few thousand qubits just to sort of hold the problem and to do the computation if you're using x squared mod n, which is probably more than devices right now have.
Okay, thanks. And maybe we have time also to answer the other question if you're willing. So there's also a question from Vinod. So again, I'll just read it. So he says, this is a very nice protocol and something quite general seems to be going on. You seem to be compiling a multi-prover game into a single prover one using cryptographic ideas. So the concrete question is this: is it possible to do something like this for other games? So for example, for the Magic Square game.
Thank you for this question. It's a really good question, and it's actually something I've thought about and also been asked about at other talks. So people seem very interested in it, and I'm happy, definitely to chat more about it if people want to think about it. What it comes down to, so I actually specifically tried, can we do a similar thing but with Magic Square? The first thing is, while this would just be interesting kind of from a theory perspective, it's not clear if it helps in terms of the implementation thing. I mean, Magic Square is nice because you get the 100% success rate for the quantum prover, but the classical one can still do quite well, right? So I don't think that, for example, I had to do this post-selection for the fidelity thing. I don't think it would particularly help in terms of improving the fidelity that you need for that sort of thing. The other thing, just, if you say, well, whatever, I'm just interested in this and I want to do it anyway, what you have to figure out is the reason that this sort of thing works is this polarization of this qubit just sort of pops out of doing this protocol. And normally you measure one qubit and then you have this other qubit and you and it happens to be in the same state as this, but there's no, at least to me, super obvious generic way to generate the states of Magic Square after one person has measured out of a cryptographic protocol like this. So, I mean, what you essentially have to do, and what I did on my whiteboard, is you can list out each of the possible outcomes of doing this measurement in Magic Square, and then try to figure out how you can get these outcomes to pop out of your cryptographic protocol. In such a way that which outcome you have depends on the cryptography in sort of a cryptographically strong way. So yeah, to me, there's no obvious generic way to do this, but maybe there's one hiding in there, and that would be really cool if someone figures that out.
Okay, thanks. Are there any other questions there in the room? I can't see, but
yeah, of course.
Basically, for this protocol, you're kind of saying if there is so any classical algorithm that passes with more than 75% probability due to an adversary that recovers the two.
Yes.
Right?
Yes.
And so here in the analysis, you can assume your adversary is classical.
Mm-hmm.
Right? Do you manage to get any handle on the state the prover holds?
That's a really good question.
If you have quantum.
Yeah. So this is a really good question, and it's something I have thought about a little, but haven't super duper explored. But this is definitely an interesting next direction, is asking, okay, yeah, Irmela was discussing, how we can use this sort of protocol to, for example, certify randomness. It's can you actually use this protocol to do a similar thing to certify randomness? And I don't know the answer right now. It's an interesting thing to explore, for sure, for sure.
okay, great. Are there any other questions? Okay, well, if not, let's thank Greg again. So thanks very much. And we're right on time, so that's perfect. So is Tony giving the talk on Zoom or?
Yeah, I'm on Zoom. I'm not in Berkeley.
Okay,
Yeah.
great. So